Project number 1 is due in about 10 days or so, I believe. So there's lots of time, but maybe not so much time ahead of us to get it done. So today's lecture will be mainly driven by walking through the first assignment jointly, right? I want to suffer with you, or I want to have the fun with you, okay? So the first project is really nice because it provides a nice break between the stuff that you have already learned in Introduction to Visualization and this new topic that I've introduced, namely higher degree polynomial interpolation. There's one particular paper that I would like to recommend for those of you who are interested in this general topic of raycasting to read. You can download it. It's a paper by a colleague named Wolfgang Krüger, and it's about the physics, the essential physics, just the essential physics that's necessary to produce correct raycast images. Okay? And just when you glance at this paper, you will see that everything that we really do in computer graphics concerning raycasting is a very, very trivial, simplified approximation of the real physics. Okay? So I let you have this and take a look at it and write down just the name of the author and the title, and you will find a PDF on the web. So now talking about computer graphics or visualization as a science, what would you have to do if you really have the approach of a scientist to our producing pictures? Okay, so here I am. I make a picture of a candle. The candle is burning. I produce a wonderful, beautiful animation of a candle burning. Okay, is this picture, this animation that I produce, correct or is it not? How do I do that? As a real scientist, how would I say this is correct? This is a correct replica of the physics that's actually going on. In physics, a much older discipline, you have experiment, theory, and simulation, right? You combine all of that. Okay, if we as computer graphics people, or visualization people, want to say, okay, this is an animation, a simulation of a candle burning. Here's the movie that I play, and believe me, it's correct. How can I convince you that my simulation of a candle burning is correct? Well, from the simulation world, I have to go to the experimental world, right? If you make an animation, a computer-generated animation of some physical phenomenon that you claim to be a physical phenomenon, you better make sure that it's correct, subject to some quantifiable measures. Otherwise, I don't believe you at all. So if I wanted to cover the entire spectrum of science and say, okay, here I have an animation of a candle burning, well, then I have to also make my hands dirty, have to go to the laboratory. I have a real candle, a certain type of wax, a certain type of lighting condition, and I let the candle burn, and I make a movie of it. Okay? I have a movie of the real phenomenon. That's my ground truth. What do I do then? Then I'm a computer scientist. I go into my laboratory, my computer lab. I write a cool program, and the program allows me to make a cool animation. When is my animation good enough? I'm not talking about correct, but I'm talking about good enough. Well, my animation is probably good enough if you have a human subject looking at the movie of the real candle burning and the movie that I've created as a computer animator, and the human subject wouldn't be able to tell a difference, right? Which is real and which is simulated. That's probably good enough to say, wow, I've really done it, right? So somehow I want to instill this desire in you to worry about making sure that whatever we do as computer visualization people or computer graphics people is correct in some sense of physics. Yeah, it's very important. Otherwise, the animations can look beautiful, but they're just pieces of art. If you cannot convince me that they're also scientifically correct, then I cannot use them for my science, particularly for, say, medical science, right? As soon as you enter a space where it's extremely important that the animations that you produce and the animation that you look at are correct, then you have to have a knowledge to do that. First assignment. Let's look at the first assignment, and there's a sheet that spells it out, right? It says project number 1. Let's go over that. And I think the lecture today will be directed at the first assignment. I want to walk us through that. Project number 1, higher order polynomial schemes. The due date is April 24, which is a Tuesday. And in terms of demo times, please be prepared to demonstrate to me in 5 minutes. 5 minutes. Because, why? I mean, I have only so much time, right? And I would like to do it directly after class. So we demonstrate here, or if someone else is coming in here, we can go just walk to the little lobby area of this building and demonstrate there. So you have to be prepared to have your laptop with you and show to me some snapshots, some image snapshots of raycast images. I cannot wait, but we cannot wait jointly for your raycaster to generate an image of 1,000 by 1,000 pixels in real time for tricubics, right? It takes too long. So you need to generate a bunch of stills, and I ask you, show me picture, show me picture, show me picture, and you can pull them up. Okay, and you tell me what you did to produce it. And of course, I would like to see how actually you run your program. So you have to be able to show me, right? I mean, this is my interface. These are the parameters I specify, and then I wait 5 hours, and then you get this image. Okay, then I just showed you, but I cannot wait 5 hours. So you have to show me the interface, what you specify, an input file or an interface console or whatever. You have to show me that, so I know how you've done that. And then you have to have some pre-generated examples there, right? And you show me, Bernd, I generated this using the following parameter settings. I generated this with different parameter settings, and I see that this is better than that, and for a certain reason. Okay. So again, think about 5 minutes, that you have 5 minutes time to make your pitch for your project, why it's good. Okay, 5 minutes. So if you demonstrate the project to the program to me, it shouldn't crash. It shouldn't require us to wait for 2 minutes for some window to pop up, right? You have 5 minutes. So show me first the cool, impressive visualizations first, some stills, and toward the end, you show me the program, how you actually use it, okay? Because that's where time consumption will come in. Raycasting methods are applied to scalar fields defined over finite 3D domains. So we have to worry about raycasting. You can go ahead and read the paper that you have by Mark Lavoie. Mark Lavoie's paper should be the basis for your first project. Several of you have already done it as part of Introduction to Visualization. You have written a raycaster already, and Mark Lavoie's paper is the foundation of all these raycasters out there. So you can use that paper and the formulas given in that paper. I put some of those formulas on the board for you. Degree of transparency, opacity. You have to worry about the transparency, opacity functions. I will talk about that briefly again today, how to do that, a very simplistic way how to specify opacities. Show more or less structural detail. The smoothness of the final image depends partially on the underlying spline that is used. Exists a point regarding the dependency. You learned about basic raycasting in 177. But if you have not learned about raycasting yet, again, I say read the paper by Mark Lavoie, and Mark Lavoie's papers really tells you about the fundamentals. That's all you need to know for this class. Okay. You will implement different local approximations to a given data set. You will implement trilinear and tricubic interpolation. So again, the basic building block in volume visualization is usually trilinear interpolation over a voxel. Okay. You know that already, you have that already. If not, read it up. What is trilinear interpolation of 8 values at the 8 corners of a cube? That's a simple way to interpolate. And then you use, in contrast to that, the tricubic interpolation scheme that I've talked about in this class. And you see that one is faster, one is slower, one is poorer, one is richer in terms of the detail that is coming out in the pictures. So that's the trade-off. Trilinear is cheap, but fast, and doesn't show detail. Tricubic takes time, but it's better in terms of image quality. So always a trade-off. V-voice method shall serve as the basic raycasting method that you can use for this project. And you need to compare images, right? Somehow you need to make, again, a quantitative assessment how these two images that you get from trilinear versus tricubic differ, right? So you have one image of a skull and another image of a skull. You somehow need to compute a difference. I talk about that in class. What kind of difference value or difference image you could compute. Must be possible to compare images using the same viewing parameters, blah, blah, blah. Your program also should support a numerical comparison and a visual comparison for the difference in those two images that you generate. Apply the voice raycasting method to data sets that have a resolution of at least 64 by 64 by 64. And again, as I said, you should begin with functions that you define yourselves. Very simple functions like f of x by z equals x squared plus y squared plus z squared, where you know that the contours are spherical shells. The picture has to look like an onion, right? You have to make sure that your trilinear and tricubic works for spherical shells. Only then can you be sure somewhat that it works for more complicated stuff like skulls, right? Okay, so you, generate some images for simple data sets that you also should show to me, because when you show me pictures of simple functions that I understand, that we understand, then you believe you build some credibility on my end, right? That I actually believe that your algorithm is correct. So show me first, when you demonstrate me, show me first pictures of simple functions, not the skull or the flame or the combustion right away. It's too complicated. I first want to see that your methods work for simple stuff, like spherical shells. So show me a simple data sets first, and then you go on to more and more complicated stuff. The user must be able to vary the from point, blah, blah, blah. I will simplify that. I will make it much simpler for you, so you can take this out, okay, of the assignment. I thought about it. A user must be able to vary from point, at point. Take this paragraph out. I don't want to make it so complicated. That will take too much time. Besides having to demonstrate your program, please prepare a simple manual sheet. Yes, I want you to do that. You have to give me a sheet, maybe at most 1 page, where you say, and the input parameters to my program are the following, parameter 1, 2, 3, 4, and the effect of these parameters when specified are the following effects for more. Okay? This is the way how you run your program. I want to know that. And additional credit, I talk about that later, when I've talked about the first assignment. Okay. Again, yes, of course, late projects are fine with me, but late projects shouldn't be fine with you because they take away time that you need for the second project already, right? So when you are in doubt whether to invest some more time on project number 1 versus using that time for already working on project number 2, my advice is work on project 2, right? You have a certain amount of time for all these projects, project 1, 2, 3, 4. Just fix the time and do the best that you can do in this fixed amount of time. Okay? So whatever the state of your program is for project 1, on the due date, or maybe 1 or at most 2 days later, say, I stop it right there. It's good enough. This is all, because you have to worry about project 2. Right? So this is my recommendation. Bottom line, on average, statistically speaking, you're better off by just always working a fixed amount of time on the different projects and showing them whenever the due date is there, period. Then the issue of additional credit, doing something that goes beyond the necessary requirements, of course. I invite you to think about, to be creative, right? You are doctorate students, graduate students. I invite you to deviate at some points from my assignment and go beyond that, right? Make it trickier, make it better, make it faster. Use a cool data set, use a cool interface, something, okay? Be creative. And of course, related to the research project that you do anyway with your major professor, okay? So I do not want to take away from your research project you work on with your professors. Whenever you see an opportunity to relate one of my assignments to your research project, relate that. I'm fine with that, okay? It's in everyone's interest. Okay, now let's talk about where we are. Tricubic Bezier, polynomials and gradient estimations and so forth. Before I go there, please ask questions. Do you have questions about the first project? Shoot.
Can we use GPU to render to do the recasting?
Yes. If that makes it simpler for you, by all means, I'm all for that. Okay. If you want to do that to get additional credit, yes, by all means, I'm all for that. Okay. If you want to do parallelization and multi-threads and all of that, fine, you get additional credit for that. Okay. Yes, you can do that. For both purposes, either to make it simpler for you because you already do GPU programming, or to get additional credit. Okay, so for either purpose. Should you get a question? No? 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 Okay. Okay, let's see where we are. Where are we? Let's reflect, okay? And it's always important to see the goal that we have in mind. The goal is a simple raycast image of, say, a skull. Where do we start? What do we have to produce? We start with a bunch of values, function values, on a Cartesian grid. I want to make it very simple now and very specific to the first assignment to help you, right? Our data are lying on an integer grid, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And I want you to produce images that fall onto the base planes of the coordinate system, i.e. into the xy plane, the xz plane, and the yz plane. Okay? So to make the interface simpler. What do we have? We have density values or function values, fijk's at the grid points or in the voxels, and at least 64. What do we need to do? We need to have gradients. The gradients do not come with the data set usually. You have to estimate them. What next? Next I said trilinear isn't good enough. We want to use tricubic per voxel. So we have to talk about how to compute the coefficients, these Bij points, the Bezier ordinates, the Bezier coefficients, for each voxel from the function values and the gradients. Once we have that, then we have to review briefly the Bezier polynomials and the derivatives, because we will need their derivatives for normals. The derivatives of these guys are the gradients, and the gradients are used as normals for the lighting computation, for the Mark-Levoy model. And then we have to review a little bit lighting, okay, the Phong lighting model, how we compute the local colors for these points, these sample points in each voxel. How do we do that? And how do we compute opacities? And this is very tricky. In this paper, I just had you guys take a look at this paper by Wolfgang Kruger, is talking about some of the relevant physical phenomena that are taking place that I don't expect you to do for this first assignment. So the pictures that you will be producing that I look at are inherently wrong, but they look cool anyway. So if you want to go way beyond that, then for your final project, for example, if you want to become ray casting specialist, you would have to do those things that are being talked about in this paper by Wolfgang Kruger and much, much more. Okay. All right, so where are we? Towards the first assignment. Towards the first project. What's given? Given in XYZ space, XYZ is a very nice Cartesian mesh of uniformly spaced samples in XYZ direction, and we call these original samples or measurements F0, 0, 0. Again, sometimes I will make the comma there, sometimes I will not. Okay, the context will give it away. In general, I will be lazy and do not put the comma there. So the last point will be Fij, k, and all the other points are numbered or indexed accordingly. So this point would be point Fi, 0, 0. Okay. All the spacing is of unit things. So these distances are always 1, 1, and 1. So we have a Cartesian data set. That's the setting. So at all the mesh points, all the grid points, we have only one value, one scalar value, one number. And we need the gradient, right? We need the gradient. Need gradients, gradient estimates. How do we get them? Again, we only need to understand how to obtain the gradient at one of these locations, one of those points. If we know how to do it for one point, we know how to do it for all the other points. So in XYZ space, we have this configuration, right? We have a particular location, ijk in terms of index, but ijk is also the coordinate of that point because we are Cartesian. And then this guy has 6 neighbors, right, in this mesh, in this grid, in this Cartesian mesh. So this guy is function value Fijk. This guy is its right neighbor, fi plus 1, jk. This guy is its left neighbor, fi minus 1, jk. This one is its bottom neighbor, fi jk minus 1. And this one is its top neighbor, fi jk plus 1. This one is its back neighbor, fi j plus 1, k. And this one is its front neighbor, fi j minus 1, k. We only, again, it boils down to using the one-dimensional formula. The gradient in x direction is always right neighbor minus left neighbor divided by 2, because this is 1 and this is 1. That's why you divide by 2, right? So the gradient estimate at well, the index is also the xyz, right? So we can say this is really the gradient at ijk. Right? The index is xyz because it's Cartesian. Is what? It will be a vector, right? I call it G x component at location ijk. I call it G y component at location ijk. And I call it G z component at location ijk. Okay, so for each point you get a triple or tuple or vector valued quantity, namely this. And what is this? I just spell it out. Where, and this is nothing new. This is just applying the scheme you already know for the 1D case 3 times. Where G ijk x equals 1/2 times something times what? Remember that? The derivative in x is right neighbor minus left neighbor divided by 2, right? So you say this. This is the right neighbor function value is fi plus 1 jk minus left neighbor fi minus 1 jk. Okay. I do not say what gy is. I only say what gz is, because the other one you can figure out yourselves. Gz at location ijk equals 1/2 of the top neighbor fi jk plus 1 minus the bottom neighbor fi jk minus 1. Okay. And now, by seeing the pattern, right, you know what gy is. It's differencing in the j index. All right, that's what we have. Now what? Now we have to build our tricubic building blocks, constructing our, these are the tricubic building blocks. Okay, so what's the situation? Situation is x by z. So again we have the original samples, and for each of these original voxels, these are the voxels, 8 in this case, a very low resolution data set, but it doesn't matter. For each of those, the original points, I called them bullets and indicated them as filled bullets. We now need to construct these 64 coefficients, right? And the 64 coefficients are arranged like this. This is a way to think of them. And we think of them, or I think of them, as circles, right? And so forth. And again, we only need to understand the game that we have to play for one box, for one voxel, because the game can be played in parallel in the same way for all the other voxels. So if you want to do GPO program or multi-threading or parallelization, this all can be done in a trivial way in parallel. Okay? So This also means that we can number these things locally with respect to the local configuration as if it was a function value f00, and this was a function value f111. This is a function value f100. This is a function value f001, and so forth. Okay, I can use a local index where I just call the lower left front corner 000. That's fine, because everyone can be indexed like that. All right, now I need these coefficients here. Blown up version. What am I after? For just this particular voxel, I need to get these 64 numbers. And these 64 numbers are the numbers for the Bezier representation, and they are the circles. This one would be B000, this one would be B300, this one would be B33, and this one would be B330, and this guy would be B033. This guy would be B003, for example. Okay? And you get the idea how the index works. Shoot.
Is this 1/4 voxel?
This voxel, but I'm only drawing the outer faces which I can see.
It's a 1/4 of one fourth of a voxel, or
no? This is this
is one voxel.
This one voxel is this one voxel, but I'm only drawing the 3 faces which you can see. Okay.
Okay.
There are 64 of those, but I don't draw all of them because then it gets occluded. Huh? All right, and so now we need to understand how these B values are related to the F values and the G's that we know at this point, okay? All right. So, compute the Bij case from the Fij case and the G values, Gij case. How to allude to that? We only need to understand how to do that in one corner, because all the other 7 corners are symmetric. I think I mentioned that game before. Okay, so this is a voxel where we need to compute these 64 coefficients, but I only tell you what we have to do with 8 of those in one corner, in the lower left corner here, because the other corners are handled similarly. So okay, you see these are 8 coefficients that are lying there, and there are 8 here, 8 here, 8 there, and so forth. There are 64 in total. And I'm only telling you how to get these guys in the lower left front corner of that entire voxel. The other corners are handled similarly. So these guys are B000, this guy is B100, this guy is B110, this guy is B111, this one is B011, this guy is B001, and you know what the name for the last one is, okay? How do we get them? Right. B000, B100, B110, And the last one I will give you B111. All right, we need function values at these guys. The function value at the lower left corner is it's a value there, the given function value there, f00. Yes. Okay. Its neighbor to the right, it's the one-dimensional case. And I talked about the one-dimensional case last time, right? How you get this first neighbor to the right. The value here is, how are they related? Also with the gradient. Remember that? The right value of this Bezier point is the value at the corner plus 1/3 times the gradient at the corner, right? In x direction. So this one is f000 plus this magic 1/3 times the gradient in x direction at location 0, 0, 0. Right? That's the gradient that we have estimated by now for all the corners, for all the voxels. And then the same for B0, 0, 1, 0, and the same for B0, 0, 1. That's why I don't put them down. It's boring, right? Except that now for the other guys, you would call this Y or Z. But the next interesting one might be this guy, B110, which is this guy. So we go 1 to the right, and we go 1 in Y. 1 in x and 1 in y. So we have to add the gradients in x and y direction times 1/3. Okay? So that's what that guy is a different type. So that's f00 plus 1/3 of gradient in x at that corner plus 1/3 of gradient in y at that corner. The other guys, like this one and this one, are similar. I don't put them down. The last interesting one is the upper right back corner, where you go 1 in x, 1 in y, and 1 in z. So just intuitively, you have to add the gradient in x, the gradient in y, and the gradient in z. Okay? That's the intuitive here. And follow your intuition, and it's f000 plus 1/3 gradient in x at that corner plus 1/3 gradient in y at that corner plus 1/3 gradient in z direction at that corner. So these are 8 coefficients, coefs, for the lower left corner, right? For lower left front corner. How many coefficients are there totally that we have to compute? 64. Are the other corners different than this corner? No, they are not. They are the same. You just have to play the game with the gradients differently, with minus signs. So, for example, at the upper right back corner here, the utilization of the gradient was always negative because you go in negative x, you go in negative y, you go in negative z. Okay, that's the way to think about it in terms of pattern. If there are problems towards the end of the class where this is not quite clear how you apply this to the other corners, ask the question, okay? All right, so now we have that. Now we know these coefficients. Now we have these Bezier polynomials, these tricubics for every voxel. And we need to do something with them. We need to sample them to evaluate them to get function values, density values for the skull. And we also need to compute their gradients for lighting computation, right? The gradient is the normal. The normal is necessary for applying the Phong model. So we need to talk about their derivatives as well. So now what? We know the tricubic representation representation for each voxel at this time. Each voxel. And so the Tricubic representation, one little heavy voxel looks like this. It has a control point B0, 0 here. It has a control point B, 3, 3, 3 there, and 62 more. So the function there is this function f of x by z, which is this triple sum, sum, I from 0 to 3, j from 0 to 3, k from 0 to 3, of these coefficients that we know now, bijk times these Bernstein polynomials, bi3 of x times bj3 of y times bk3 of z. Where we always assume that this is x direction and this is parameterized between 0 and 1. This is y direction. This is parameterized between 0 and 1. And this is z direction. And this is parameterized between 0 and 1. Okay. Now comes a little intermission about Bezier polynomials, because you need to have a module somewhere in your program where you compute values of these Bezier-Bernstein, Bernstein-Bezier polynomials and their derivatives. These are just modules that you call over and over again. So this is just a note or remark. Note definition of Bernstein, Bezier polynomials, and namely their function values and derivatives, FCT values and their derivatives. So somewhere in your program you need an arbitrary function that you call with the parameters I, the parameter n degree, and the location where you evaluated at x, right? So somewhere you have Bernstein polynomial with arguments I, n, and x going into it and returning the value of b. Huh? So, and this one is just defined as n choose I times 1 minus x to the power of n minus I times x to the power of I. And we assume that x always varies, for our simple case, between 0 and 1. Everything changes once you're dealing with grids which do not satisfy this, okay? Talk about that later. So what is this? This n choose I will spell it out for you one more time, even though you told me what it was last time. It's n factorial over I factorial times n minus I factorial times that stuff, 1 minus x, n minus I as power, and times x to the power of I. That's the polynomial. Fine, you can call this thing over and over, right? And that's all you need, really, for most of it, what you have to do. But you also need the derivative. Why? Well, we need to compute gradients. Gradients are the normals and so forth. We need to know what the derivative of the thing is. So this is the first. You also need to understand what is the derivative d dx of such a thing, bin of x. And we can just say that is bin of x prime, right? And I give you the result. You actually can formally derive this, what the derivative of one of these guys is. It is see. And I say, see the Farron book for the derivation of BINX prime. And I stop there. Okay. These are the two things you have to look up in the Farron book or any book on geometric modeling where Bezier curves are discussed. Okay. When we take home messages, we only need to have a module where we compute BIN and a module where we compute the derivatives for this guy. Now we have a function. In the 1D case, we have a function f of x, which is sum I from 0 to n. I do it for an arbitrary n of coefficients bi, bin of x. Okay. The bin of x's are defined like that. And what do we need to know? The derivative of this function, deriv of fct is what? And the derivative of this thing follows from formally actually deriving this. Once you do that, after a lot of manipulation, you get the derivative f prime of x. And the interesting thing is it has a similar form. It is n times the sum I from 0 to n minus 1 of certain differences, bi plus 1 minus bi times Bernstein polynomials bi of 1 degree less n minus 1 of x. This is the most important thing that we need for our first assignment. Okay. We have a function defined like that. Bezier coefficients times Bernstein Bezier functions, and we need its derivative, which is like this, n times, and this n times is very important. N times a polynomial which is of degree 1 less. Why does it make sense? Well, it might make sense because when I differentiate a polynomial of degree n, the derivative must be 1 degree less, okay, intuitively. So this all makes sense. Again, to get this formally, you need to do all these derivations, and again, that's done in the books and takes multiple pages. Okay, but why do we need this? We need this for the trivariate setting, right? The 1D case doesn't even do it. We need to do it for 3D because we want to compute normal vectors inside the voxel because we want to do lighting. Okay, so now I have to really give you the result, how you differentiate the function defined over the voxel at any arbitrary sample location inside the voxel. Okay, and again, the one-dimensional case will suffice because we just have to apply the formula in the 3 directions, in x direction, y direction, z direction. That's the beauty of the whole thing. Okay? You only really need to understand the 1D case, and then you apply it for the 3D case by using it 3 times. Okay. We need gradients for this, for star. Right? This is the function. This allows us to evaluate at arbitrary locations inside the volume a function value, a density value, a scalar field value, but you also need a normal there, and the normal is a gradient. Need to compute gradients of f of x, y, z. How do we do that? So the gradient f is given over there. F of x, y, z is that formula star. And now we need the gradient. The gradient is the grad of f x, y, z. Is also denoted by this grad symbol, gradient symbol, grad of f x, y, z, which is formally the vector of the 3 derivatives. So it's the partial derivative b dx of f, the partial derivative with respect to y of f, and the partial derivative with respect to z of the function f. So it has 3 entries. And now I just give you the result, what this derivative is. And it will become very simple when we consider the expression at the bottom on that board. So we need an abbreviated notion for that. That's too many symbols. I just call this f sub x. I call this f sub y, and I call this f sub z. So these subscripts denote differentiation with respect to the three spatial variables, okay? And then I have the following. F sub x equals something, f sub y equals something. I will not give you that because it follows by patterns. You always have to see patterns in this whole game of mathematics. So f of x equals, it's n times the sum of something, coefficients times Bernstein polynomials of 1 degree less, right? So it has to be, because our n is 3, it has to be something like 3 times 3 sums, and it's a difference, and now a difference in the x direction. It has to be bi plus 1 jk minus bijk times bi of 1 degree less 2 of x times bj still cubic of y times bk still cubic of z. And the coefficients I from 0 to 2, j 0 to 3, and k 0 to 3. Okay. What happened here? I applied this differentiation just to the one component, the x component, the x direction. Right? So it's n times, n is 3, we deal with cubics. It's n times the sum. The sum has to be a difference of coefficients, well, the difference in the x direction. So the difference has to be in the I index, I plus 1, minus I. The rest stays the same. And then the polynomial degree goes down for the polynomials in x, only for those, because they only differentiate with respect to x, not with respect to the others. Okay? And then therefore also the index for I has to terminate at 2. The others still go up to 3. So now by pattern, you see what fy has to be, and fz, I'll give you that. So fv is the same game, 3 times a triple sum. Which one goes up to 2 in this case? K from, well, it has to be k, right? K is the third index, is z. This goes to 2, this goes to 3, this goes to 3. And the differencing has to happen in k or z direction, or the third index. So it has to be bij k plus 1 minus bijk times which degree goes down? The degree of the polynomials in the variable z, because I differentiate with respect to z. The others stay the same. So it has to be bi3 of x times bj3 of y times bk2 of z. These are the ones that I need for my normal computations. Now we have everything that we need in terms of machinery to do our pictures. And now I talk about the picture making. Is everything clear so far? Does everything make sense? Everything is rather simple. You only have to see the pattern in all these formulas. These formulas are very long, but there is a very distinct pattern to them. In the index, in the directions, and it's always the same. It's always a one-dimensional case played over and over again in the different directions. Okay? All right. So what do we do now? Bernd is nice, and Bernd says, make pictures only for planes, for image planes that are aligned with the coordinate system planes, to make it simple. No arbitrary viewpoint, no arbitrary orientation. Just give me a nice bounding box of your Cartesian mesh and throw this raycast image onto the xy plane, the xz plane, and the yz plane, okay? So, project number 1. And now it becomes specific. What do we have to do? Okay. The setting, and this is good enough, and it will illustrate it just for the 2D case. Setting, raycasting raycasting for Cartesian meshes only, Cartesian meshes, and I use the term projected onto the coordinate system planes, projected onto the coordinate system planes, coord system planes. And so those planes would be the xy plane, the xz plane, and the yz plane. Now I illustrate that for the 2D case, 2D illustration. So in the 2D case, we have our very nice, happy and simple Cartesian mesh of resolution 3 by 3 grid points, or 2 by 2 voxels. This is a grid point, right? This is a voxel. There's a duality. And then I say you can throw it onto the planes that are parallel to the bounding box planes. So it's absolutely fine if you just produce pictures where you use the image planes being parallel to a face of the bounding box. So in the 2D case, there are only two natural projections, right? One in x direction and one in y direction. So these are the pixel planes or image planes. In 2D, you only do a projection onto x, or ray casting onto x, and the ray casting onto y. And so the viewer, in this case, tends minus infinity in x, and in this case, the viewer tends minus infinity in y direction, right? What do we have to do? These locations are the original grid locations. This would be 0, 1, maybe n, and this is 0, 1, and n. So you have n plus 1 squared grid elements and n squared voxels. What is the elementary operation we have to do? This is the elementary operation. We have one particular ray going through the volume, and we need to determine what is the color here, right? That is the whole game. What do we do? What do we have? We have to compute samples along this ray, many of them, maybe between 6 and 8 for your tricubic case, okay? So you compute these locations. And we compute these colors there. At each of these locations, we compute the local color, Ci, and then opacity, alpha I. And then we sum all these things up in some kind of form according to the Mark-Levois formula to get the color there, right? That's what we have to do. So this is one of those cells, and I will blow that up. What's happening just in one of those cells? It's the same all over the place. You can do this in parallel, right? You can generate these rays, or you can produce the colors for the pixels in parallel. If you make an image of 1,000 by 1,000 squared, if you have 1,000,000 processors, right, each processor can do 1 pixel, right? Boom, you get instantly the response. That's nice, but we don't have a 1 million processor machine yet, at least not in our pocket. So I blow this one up. What's happening there? We have this one particular voxel, which I just draw as a 2-dimensional square, and we have a ray going through it, and we have a sample point. We need to compute, for this sample point, must compute two most important things, namely the local color, color I, local color, and the opacity, alpha I, opacity. And you've done this already. Those of you who took Introduction to Visualization have done this and played with this magic. Okay? And there are many, many more samples to the left and everywhere along the ray. So all we need to understand now is how to apply a lighting model there and compute a color. We have to really ask ourselves, what does it mean to compute a color for a point that lies in a volume of more or less a solid material? What does it mean? I know how to compute a color for this. This is the surface in three-dimensional space, right? The outer surface of some kind of solid material, right? What does it mean to compute a color for a point in the interior of this solid material? Huh? It becomes very complicated, and it's not simple at all. But in a trivialized sense, people do it as follows. We talk about one color Ci. Okay, and now you guys have to help me how we do that. So here's the ray, here's a point, and the local color Ci equals what? How do we get the color there? Many of you have done this already. How do you compute the color at the sample point in the volume? Be brave, anyone. I've forgotten this. I did this 30 years ago, so I've forgotten all of that. Come on. What is the most popular lighting model, illumination model in all of computer graphics? Has a name, right? Phong. So we apply the Phong model there, right? What do you need to compute a color based on the Phong model? You need to have, what are the ingredients? What goes in there into your Phong routine? Be brave. Give me something. Ambient color?
Normal.
Huh?
Normal.
Normals?
Lighting. Angle.
Specular, angles, various angles, light intensity, light source position, reflection vector, viewing vector, Phong constants, degree of specular effects, metallic behavior, all kinds of stuff, right? So the Phong model, now that you have talked about it, it's coming back slowly, right? My neurons are now getting reconnected, and the things are coming back even for me. So the Phong model. All right, so I just give you the formula. You find it in the textbook, right? This is a textbook notation. I don't like it, but anyway. Textbook notation. So the textbooks talk about an intensity at the sample point P. So this is my sample point P. And at the sample point P, I have a certain local configuration. The local configuration is that there exists some surface. Where does the surface come from? I'm talking about the volume. Where's the surface? It's another magic, right? It's the volume. Where's the surface? I apply lighting model, Phong model. The Phong model is a model to illuminate points on surfaces. Where's the surface? Okay, well, anyway. So we computed something very magically that was this normal vector, right? The gradient. This gradient thing is used as the normal. Okay? So this, in fact, defines the normal. The normal n, is now defined as this vector consisting of fx, fy, fz. Okay? It's not normalized yet. It's still arbitrary length. You have to divide by its length. So we have a normal there. Then there's a light source somewhere, right, in the Phong model. Then there's a vector that goes from the point being illuminated to the light source. It's what usually called the light vector, right? Then there's a view vector, the vector from the point to the eye. And of course, that is the direction of the ray itself. So here's the view vector. And then there's a reflection vector, right? Light coming in like this, tangent plane, then light being reflected like that, right? So there's a reflection vector, R. And then there are angles between these things, right? So I of P, there was an ambient color, intensity of ambient light times some K sub ambient, plus there was something like this. Different textbooks have different formulas, actually, and contradict each other. But anyway, there's something called I, that's the intensity of the light source. Light source has an intensity, and then you divide it by some kind of distance term. Usually that's modeled by some kind of constant, some constant plus some kind of distance between two things, between the eye point, the viewer, and the point itself. So here's the eye point, E, eye point. So distance between the point being illuminated and the eye. And then this is multiplied by something which is the diffuse color, K sub diffuse, times a vector, times the dot product between the normal vector and the lighting vector, dot product L, plus the specular coefficient, K sub S, times the dot product between the reflection vector R and the view vector dot V to some power P. You remember this formula vaguely from computer graphics? It's in the books, right, Sambhya? Everything that I talk about is in the books anyway. You don't really have to copy that. Only really have to, Bern said, to compute a color there, apply the Phong model. The Phong model is in the books. And there are 50 different ways to write this Phong model down. Okay, this is just one way to write it down. So the color at the point is some ambient color. Now we have to understand it, what it means in the context of illuminating volumes. The Phong model was to illuminate points on surfaces. Huh? Now we have to make a transition. We apply this Phong model, not really applied for our purpose, to the setting of volume illumination. Okay, Phong model talks about three terms. It talks about ambient color, it talks about diffuse color, and it talks about specular color. The ambient color is a color that is kind of like in the background, a mixture of all kinds of wavelength. If I were to turn off the light switch there, then what is left is the background color, the ambient color. Ambient. Then there is a diffuse color, which is the color of the object itself. So this would be black. This would be purple, right? And so forth. So K sub D is the color of the object that we illuminate, and K sub S is the specular color, i.e. the color of the light source. And then everything gets modulated by the intensity of the light source and the distance between the point being illuminated and the viewer. Because the further I'm away, the smaller is the intensity that I perceive as my eye, because the photons have to travel, right? They travel in spherical shells. All right, so again, N is a normal vector, L is a light vector, R is a reflection vector, V is a viewing vector. I don't want to spell them all out on the board. You find it in the books. You apply the Phong model. There's a point, a sample point in the volume. You need to compute a color. In order to compute the color, you apply the Phong model, period. No further questions asked. Correct? No, you have to ask questions. What does it mean to use the Phong model for a volume? A Phong model is for a surface. What the heck is it doing any good for illuminating volume? What does this mean? Now you have to ask the question, okay, I have this translucent jello, right? I have a transparent medium, but it's a solid thing. What is the ambient color of a solid thing? Well, that's the ambient color that's floating around in the interior of that volume. Okay, so you have to, what does it mean? If I have a jello, a green pudding, whatever, okay, it's a green something. Well, the ambient color in this green something is, what is it? Is it green? I don't know. Green is probably its own inherent color. It's diffuse color, right? Diffuse color is the color of the object, right? A color of an object is the color of the photons that are leaving that object, right? Jello is green because the green photons are coming out of that thing. So K sub D in the context of volume modeling has to be the material property that you illuminate. Okay? If it's a green transparent jello, then it's green. If it's a yellow jello, then it's yellow. You make it up. If it's a human skull, what is it then that you illuminate? Becomes more difficult, right? K sub S is the light source color, okay? The vectors are defined as they are in the text box. So we just apply the Phong model to sample points. Along each ray, right? But again, each parameter coming up in this Phong model deserves its own interpretation in the context of illuminating volumes. It's not trivial at all.
I have a question.
Sure.
I'm assuming this is unitless?
Yes.
Okay, so things are normalized.
At the end, you get some numbers, and then the biggest, you divide everything by the biggest number, and then it's normalized, right? Yeah. I'm not even talking about units, yeah.
Question too. So you're explaining how these parameters make it sort of strange to apply the Phong model. Mm-hmm. But what's really strange to me about it is that if you just think about it, the light, it comes through the surface first.
Wonderful, wonderful. Yes, I talk about that too.
Okay.
You're on the right track. Yes. When you're in the orbit of the Earth, you perceive the sun of a certain brightness. When you're on the orbit of Pluto, you perceive the brightness of the sun to be much less. That's one phenomenon. The other phenomenon is when you illuminate a point in the interior of a solid material, the photons that had to reach this point, that the length of the path to reach this point is a different length than the photons that had to reach the point here. Because the photons from that point light source travel here, travel there. Many, many different things that come into play that actually have an effect. Again, the ultimate test whether your raycaster is good or not is to actually do the experiment. You have to go into a real lab. You have a candle burning, right? You take a movie, you take your camcorder and make a movie of a yellow candle of a certain type of wax burning. And then you try to model it with the stuff. And you're done when your animation cannot be distinguished anymore from the real movie, okay? And then you're done. When you're not there yet, then it's not done. My animations are not done, okay? All right, so lots of questions. And I cannot give you all the answers to that, okay, how to do this better, but this is the way it's done. Apply the Phong model to the lighting. So this is the most important part. This is the inherent color of the material. Okay. And then comes the other aspect. Number 2 are the opacities, opacity computation. Opacity. How do you get the opacities? How do you get the opacities? A simple scenario. This is where this raycasting came from anyway. Simple scenario. When you go back to the Mark Lavoie paper and you read it, there are skulls in there, right? So it comes out of the origin of raycasting visualizations lie in medical imaging, okay? So in medicine. So the data sets had an inherent physical meaning. They were CAT scans or MRI scans of human skulls, okay? So when you make images of the human head, there are certain types of materials that you're dealing with. There's air around me, there's flesh, muscle, and there's bone, and there's gold in my teeth, right? In my teeth, not in yours. So, all right, that's how you define opacity. Well, you keep that in mind. There's this inherent notion of density of certain materials. If I have a CAT scan of this head, I have values for flesh, values for teeth, values for bone, and values for gold. Okay? And the underlying assumption is that when I'm illuminating this stuff, or shining X-rays through that, CAT scan, computerized axial tomography, then I can interpret the function values I get as densities of certain materials. And I make images, that's what Mark Lavoie does in his paper. I make images based on the paradigm of assigning higher opacity to denser materials. The denser something is, the less light it allows to pass through it. Okay? So that's the most trivial way to assign the given function values to opacity values. F equals opacity. That's the most trivial way, right? And that opens up this entire game of transfer function design. What are good transfer functions? Again, there's no conclusive answer to that. That's an entire art in its own right. But it really should be a science, not an art. So medical data sets. Medical CAT scan data set. CAT scan, computerized axial tomography scan data set. And I illustrate that here with Mr. Happy. Okay, it's in there. And so there are 3 types of materials, say, right? 3 types of material. Okay, so there's air, there's flesh, and there is bone. And the paradigm for transfer function design, or opacity design, paradigm. The paradigm is given function values are densities, and the denser something is, the more opaque it is. Given function values, given FCT values, Fijk, represent densities, represent material densities, semicolon, the denser something is, the denser a material is, the more opaque it is. The larger its opacity is. Is this correct, the statement? I don't know. Is this a statement that works in practice pretty well? Yes, it does. So example, you could have unity function where you have the given function values on one axis, FCT values, they are given, and you need to assign opacity. And opacity, the way I've done it, or the way Mark Lavoie does it in the paper, is always between 0 and 1. Opacity 0 means completely transparent. Opacity 1 means completely opaque. Right? So opacity is bounded by 1. And the simplest way of doing that, if your highest function value is 1, you normalize everything, right? You can normalize all the function values to the range 0 or 1 by dividing all the given positive values by the maximum value. We just do this, right? This line embodies that principle over there. If something is of low F value, of low density, all light goes through it. If something is of high density, of maximal density, 1.0, no light is going through it, therefore it is completely opaque, non-translucent. So this would be alpha, the opacity, which depends on the input values, the F values. But sometimes, so opacity equals FCT value. And this gives very good pictures already, or interesting pictures, meaningful pictures for medical data sets of all kinds. But then more interesting, assign specific opacity values to specific materials, but that requires some user knowledge. Okay? You assign different opacities to different materials. This goes in the direction of transfer function design, and I'm just hitting on it. Transfer function design. So say in the case of a skull, opacity, you know that flesh produces function values in a certain range. Flesh always gives you a function value in this interval. Then you can give this a certain flesh-specific opacity. And you know bone is much denser, and you know that bone in my head always gives function values in this range. Therefore, you can assign a bone-specific opacity for bone. Okay? So again, alpha of f should be bounded by maximum opacity of 1. You can say, well, I know that in this range, things are flesh or fat. Things in this range are bone. The rest I don't care about. You can completely eliminate it. Elimination in the picture means making it completely transparent and therefore not show up. So you can say my transfer function is 0 everywhere until it's in this range that is the fat range or the flesh range. Then it's 0 again, and then I call it higher opacity, denser, because it's bone. I call it, say, bone. And then it should go down to 0 again because I don't care about anything that is gold in my teeth. Okay, so I want to have that be completely transparent and be gone. I make it gone by taking it down to 0. So say I know what the function values are in a CAT scan that correspond to fat. There's a certain interval. I know what the function values are in a CAT scan that correspond to bone between this and this value, and only those two things I want to see. Therefore, I give these two ranges opacity values different from 0, or the rest I call 0. I don't want to see it. So this is fat opacity. It's bone opacity. That's fine. And then you can do much, much more. But I need to stop there. Much more. Now I need to see whether I need to tell you more about the first assignment. The first assignment, yeah, I need to tell you one more thing that is on the assignment sheet, the difference image, right? You want to assess what kind of picture it is that you get when you use trilinear cells versus pictures that you get when you use tricubic cells. The pictures will look differently. You can show them to me. You will show them to me side by side, but I also want to see a difference image, right? How do you difference the images? We'll talk about that very briefly. It's quite easy and straightforward. Showing the differences that you get from trilinear versus tricubic. It's a comparison, and you only compare two, trilinear versus tricubic voxels. Well, you do one pass, trilinear, and you get a picture for the tricubic case where you wait much longer. And you get, in your pixel plane, your image plane, you get your happy smiley face. Okay? When you do tricubic, you should see more than that. Or do you see less? You also get a picture. Okay, there will be differences. What do you do? Well, you compute color values, right? For each pixel, this is just the image plane, ij. These are the resulting images. And I don't know what the resolution is. Maybe you go up to 255 or 512, maybe 512. 512, 512. Well, then we call this 511, right? And this is 0, 0. And here you also compute a pixel, and these guys have certain colors, right? So at each pixel you will have a color, a red, green, blue, triple. So here you will have a triple, call this for the first color Rij, green Ij, and blue Ij, because you have to do it for the 3 color channels. And here you do the same, but this is the second method, so I call them small Rij, green Ij, and blue Ij. Again, RGB, red, green, blue. Okay, shoot.
Why wouldn't we have RIJK in the tricubic?
No, this is just the image. This is on your screen. This is on your screen. You produce one picture here, one picture here. They are now in the plane, on the screen, okay? So, and I want you to compare the 2 pictures. You show them to me side by side, and they already will look different, okay? But now I want you to quantify it. There's a difference image. You can produce from these 2 guys a difference, of course. How can you define meaningful, in a meaningful way the difference of pictures? The difference of pictures are the differences of the colors per pixel, right? So what is the meaningful difference for pixels?
Subtracting them.
Subtracting them, right? Right? So this might be 15, and this might be 27, right? So I do 15 minus 27, right? Which is minus 12. So the difference image will have a red value of minus 12. Absolute value, maybe. Okay? So we don't run into negative colors. Okay? So we could say the diff, you could say the diff value at ij could be also a triple. Say it is the absolute value of rij minus rij, and then the green difference, green ij minus green ij, and then the last component would be the difference in the blue, blue ij minus blue ij, absolute value, okay? But a color difference image might not be a good way to show it. You just really are interested in some kind of one number, a grayscale, okay? Okay, so you can think of this now as a vector, right? This is a vector in RGB space. RGB space is an RGB cube. It's in the color model, RGB. This is another point in the RGB cube. You just want to know the length of the difference vector, the distance vector between this RGB triple and that RGB triple, and then you just have one number, right? Or you can just say the difference dij is just the square root, it's the length of this difference vector of rij minus rij squared plus the difference in green ij minus green ij squared plus blue ij minus blue ij squared. Okay, that just gives you a number, the length of the vector of these 2 triples in the RGB color cube. And then you can make a grayscale picture of that. You can quantify it in other ways, okay? But at the end of the day, you need to assess somehow what the difference is. And you want to show it. It would be particularly cool to show in which regions of these images, of these pixel spaces of the planes, the differences are really large, and in which areas these differences are small. Because then you get an understanding for what types of behavior you really need a cubic scheme, and for what type of behavior you don't need a cubic scheme, right? All right. I will stop here and I take your questions. Please ask me your questions about the first project. Ask me the question. Your questions are his questions. Shoot, give me two.
Okay.
Bonus point.
Sure. You mentioned numerical comparison for as well as a difference image. So would a meaningful numerical comparison be the number of pixels that are different? Hold on, I'm trying to think of another question.
Right. The entire toolbox of statistically defined measures could be used. Okay. So yes, you could. You will compute the difference values. There's a difference value at the bottom for each pixel, pixel by pixel. Then you can compute things like what is the minimum difference I have between pixel pairs. That might be 0. What is the maximum difference I have between pixel pairs? It might be a big number. What is the average difference that I have going over all the pixels? Sum all the differences up, divide by the number of pixels. Then you have root mean square error. So what is the root mean square error? You sum up all the difference values, you square them up, and you divide by the number of total pixels, and you take the square root of that, which is another statistical measure. It's called root mean square difference or error. There are many, up to you.
Okay.
Convince me that you have a good, statistically meaningful way to assess the difference between two images in just one number. Ultimately, you just want to have one number that characterizes the difference, right, between two entire images. But it is from a raycasting science perspective, more important to understand in what regions you have the larger differences and in what regions you have the smaller differences, right? Okay. Did it help?
Yes.
Okay, that was the first question. Give me a second one.
That was my only real question I could come up with.
You can do better. I have so many questions.
Thanks.
For the simple, I don't know, maybe not simple question. So for the Phong lighting model, I mean, so especially for the ambient color, should we just mess with it and see what happens?
Yes, you mess with it and figure it out, right?
Okay.
Again, there are many papers out there that discuss how a Phong lighting model-like method is applied to illuminating volumetric data. Okay? There is no standard way of setting these things. When you restrict yourself to the pure Phong model, you have to figure out a definition for ambient light. But then you have to think about it, right? As a programmer, as a scientist that you are beginning to be, right, want to be, you have to think, what does this mean? The ambient color of a region in space in a volume that is a translucent medium. What is ambient there? Well, it's the photons at all the wavelengths, at the things that are just bouncing around, right? What is that color there? If I have white light coming in, then there's all kinds of phenomena taking place. Absorption, reflection, refraction, emission, quantum effects, going to higher levels, falling back into lower levels, certain wavelengths, all of that. Make it simple, make it meaningful. Play with it. If you think this ambient stuff doesn't make sense, it produces meaningless pictures, and it can only add to confusion, you make an argument that you should not consider it. Boom. Fine. If the Phong model is just simply too complicated and cannot be understood in the context of illuminating volumes, make it simpler. Actually, it's much more complicated. The other issue is, and then I want to stop, the other thing is, of course, and I think some of you were hitting on that, I have a solid, I'm living here, I have my eye here, here's the light source. I'm illuminating this, right? The heavy photons coming from the sun, they are traveling on shells. The further I'm away from the sun, the less intensity I see. But these photons, they are hitting at different entry points the material. And then there's all kinds of absorption happening here. Okay? This is not really modeled by most raycasters. That as soon as this light is traveling from here to the entry point of the solid medium, then all kinds of absorption is happening. The intensity of the light, the energy that reaches this point, is greatly damped or reduced by the very fact that these photons already had to travel through a solid medium. So you really have to do a raycasting also from the point to the entry point to see how much light, how much energy actually can reach this point when the light is coming from there. Okay. And then the ultimate challenge is a real-time burning candle. Do that for me as a final project. An animation, a simulation of a real-time burning candle where I can fly around it and see, okay? Maybe you can do it. Thank you.